both models are very representative example to show age transition and critical phenomena. It applies for both cases. And percolation, more like a pure mathematics problem, is deal with this kind of random feeling of any kind of a spatial or non-spatial structure, and it will have this kind of a cluster structure. So the control parameter here, occupation probability P, and order parameter here was the size of the giant component or size of the percolating cluster or largest connected component in numerical sense. So size of percolating cluster. There are other things here as well, but I would like to give the most essential part here. So depending on the dimensionality or other topological aspect, it can have some kind of a phase transition, or at the very end of the control parameter range, which is correspond to the one-dimensional case. So usually, as the occupation probability increases, we have this kind of so before this critical occupation probability, in the infinite size limit, there is no percolating cluster, so it's zero by definition. And it suddenly pick up like this. And this particular behavior is actually characterized by this kind of power law behavior. And the beta here is the critical exponent. And that depends on the dimensionality and etc. And of course, the peculiar case or singular case is the one-dimensional case where PC is actually 1. So there is no such percolating part in one-dimensional system. The Ising model is a real physics model, and it describes the spin-up or spin-down system. It starts from some kind of structure, regular or irregular, and in variable, up, down, down. Sure. One thing that's missing from this percolation problem is definitely this energy term or Hamiltonian term, which makes this Ising model the real physics problem. Is that this energy function for a given spin structure, as I already emphasized, this curly bracket actually represent the collective term for all the possible spin configuration. So it's usually correspond to this. So I already write down here. Minus h I plus I. So it's usually only deals with the nearest neighborhood, and it contributes the plus energy or positive energy for the anti-parallel spin and negative energy for the parallel spin. And this is an effect of the external field, where if a spin is aligned with the external field, it will give the negative energy, while the positive energy for the otherwise, if the spin itself is anti-parallel to the external field. So here, control parameters, actually, there are two major control parameters here. One thing is that, of course, this external field. And you may say that J is also another control parameter. But actually, we usually consider the temperature as a control parameter because this temperature would govern this system by the fact that some kind of states or the probability for a specific spin state is given by this canonical ensemble. And here, beta is just the inverse temperature, except for this Boltzmann factor. So we don't need to worry about J here because if you consider this factor, this part actually include J over T and H over T. So once you decide H and T value, J is just a controlled overall constant factor. So it doesn't really matter. So that's why we usually talk about the H and T here. So this energy term is also can also play the role of order parameter, but more important order parameter here is the average magnetization itself. So kind of average value. So how much the fraction of the upspin, the relative fraction of the upspin and the downspin. And of course, since there are two control parameters, the problem is rather complicated, but we are usually interested in the fact that, for example, in the absence of this external parameter, is it possible to have this ordered phase? And the answer is heavily complicated. So that's why we had this whole chapter devoted to that. So basically, I mean, compared to this mathematics problem, we have a relatively well-established framework of equilibrium statistical mechanics, which is calculate the free energy. This one. And from this Helmholtz free energy, we can derive lots of different things. For example, we can use the derivative to produce M for energy, or susceptibility, for specific heat, etc. So the only thing necessary is to calculate the partition function, of course. So this partition function, it looks like very simple summation, but it's actually not quite easy to actually calculate, because if we spell out this partition function, it's actually plus j ij sij plus beta h si. And as I already emphasized quite a bit, the most non-trivial part is this one. So this is the problematic part. Because this can be heavily irregular sum. Where in contrast, this is a completely regular sum, just a linear combination, just a linear sum without any weighting factor. So that's why the first thing we try is not the one-dimensional case, but the paramagnetic case, where paramagnetic case corresponds to J is equal to 0 simply. So in this way, this is reduced to this. And this summing over everything can be actually separated because it's a summation inside the exponential. So it's a product of the exponential, etc. And this is a sum over every possible spin configuration. One can be plus or minus one, and S2 can be plus one or minus one, and Sn can be plus one or minus one. So this unrestricted product over all the unrestricted summation is actually same as this kind of summation. And for all of these n factor, this S1, S2, or any kind of spin variable is just a dummy variable. So it's just twice the cosine hyperbolic. And all of these vectors produce exactly the same functional form, twice the cosine hyperbolic. So it's the nth power of that function. So it's super simple. So Z is very simple. So F is very simple. So you can calculate everything. So including the very nice result that this magnetization should be tangent hyperbolic of this one. This paramagnetic case is so representative, so I even remember this without looking at any note. But yeah, this is a quite important result. But in reality, we have to actually do this. So the first thing we actually tried was, this is very nice because it's exactly solved, but not something we actually expect. And especially there is no phase transition whatsoever. In other words, any non-zero at any non-zero temperature, there is no spontaneous magnetization. And the only result is this. If H is 0, you will have a 0 magnetization because because of the functional form of this tangent hyperbolic. So the next step was one-dimensional case, where now this summation become single sum, at least for the single sum, but Si and Si plus 1, just right next to each of the spin variable. So it's from, and one tricky part is that if we write like this, there can be Sn plus 1 spin, which would be the same as S1 spin if we apply this so-called periodic boundary condition. And this problem is a little bit, perhaps not little bit, more complicated than this single summation. So we needed some kind of a transfer matrix technique, etc. And we need some kind of knowledge about linear algebra. So we actually get some results. But still, even in this result, there is no phase transition except for t equal to 0. So just like the percolation problem, for one-dimensional system, we don't have any phase transition, or at least a non-trivial phase transition. We still, up to this point, we still don't have any theoretical model to reproduce this spontaneous magnetization. So instead of directly going from one-dimensional case to two-dimensional case, which the problem become much more just a much more complicated problem. So before we do that, just like we did for the one-dimensional case to better lattice instead of two-dimensional system, we actually move from one-dimensional system to not two-dimensional system directly, but we will try to find this so-called mean field approach. In fact, it is possible to going from one-dimensional Ising model to Ising model on better lattice, which is actually also exactly solved, and also I can recommend some reference for that. But for the sake of the pedagogical reason, I follow the textbook's approach that introducing the mean field approach first. So that was the initial point of this lecture note, mean field theory of the Ising model. So the key point was that the key ingredient of this mean field model is that instead of looking at all of these complicated interaction from this ice spin perspective, let's just treat this entire spin into a single large spin. And let's only consider interaction between these two. And of course, the problem is that the reality is this one, but you ignore all these so-called local fluctuations. So how can we actually ignore this local fluctuation in the real actual calculation? Is that first rearranging this energy term by just identity. This is just an identity by subtracting this one and adding this one. Then this particular format represents the deviation of the spin variable compared to its own average value. So if you do that, and if we actually ignore this local fluctuation term, we will have this form. And the great thing here is that by just summing over all the nearest neighbor interaction term, we can actually replace this real interaction term with the average spin variable multiplied by the number of nearest neighbor, which is which we usually write as k in network science language. So by using this kind of heavy approximation, now we just convert all of the source of all the complication, this angular bracket term, we just get rid of this angular bracket term. And we only have this single summation term, which is straightforward. So by using this single summation term, we can actually derive this free energy, the partition function. And based on this partition function, we can actually calculate the free energy or free energy per spin as well. So this is the result. And the formation or the functional form of this mean field free energy actually show this kind of a non-analytic or non-differentiable part here, which would correspond to the singular part or non-analytic part characterized by this cusp shape. It's like the paper is like folded like this, non-analytically folded. So in this way, we calculate all the different things. And the most important thing here is that this particular functional form give the magnetization or spontaneous magnetization term. And if we actually, I just omit all the complicated calculation, but I will just write down the result. So this looks quite similar to the paramagnetic result because it involved the tangent hyperbolic. But there is actually very big difference than it looks because this equation says that if you have some kind of temperature parameter and external field, the magnetization is just determined. There's no complication about it. But the problem here is that suppose you have this mean field so-called solution. So this is mean field solution. But I put here the quotation mark here because even if we know beta and H, and of course J and C, the problem is that to actually get the number for magnetization, we need to know about magnetization. To know this, we have to know this, and yeah, this is kind of circular argument. So this is a so-called self-consistency equation. Of course, there's a standard way to actually or numerically get this thing because so suppose we have zero magnetization case, then this one, and this is actually the actual value that satisfy M here can be obtained by first setting this M is equal to M line, or actually 45-degree line, tangential line, and this hyperbolic tangent line is always bounded by -1 and +1. So you can either have 3 solutions, or depending on the shape, just one solution. In the latter case, the purple line case, purple curve case, the only solution is M equal to 0. So there is no magnetization, no spontaneous magnetization. And that would correspond to this smaller value of beta. Because of this functional form. So smaller value of gamma correspond to higher temperature. So there is no magnetization in higher temperature, which is consistent with our intuition. And for larger value of beta, we can have some non-trivial or non-zero magnetization, which is actually also consistent with our intuition that there can be spontaneous magnetization at a lower temperature. And perhaps more importantly, we can actually exactly pinpoint where this transition happened. And of course, the criterion of these 3 different crossing points versus single crossing point is determined by the slope of this tangent hyperbolic function at the origin. So if you look at this blue curve has the slope of larger than 1, and this purple curve have slope of smaller than 1. So of course, the critical point posed just right in the middle of these 2 criterion should be, so the TC criterion should be considered as a slope of 1 for the tangent hyperbolic function. And this tangent hyperbolic function, if you take a derivative and calculating, the slope here is actually beta. No, it's not beta. Sorry. Slope is actually beta j c. So the critical temperature should be given by, so beta c, or the inverse temperature or inverse critical temperature should be given by this criterion. And since beta c is kBt 1 over kBt times Tc, you can actually get the result where Tc should be like this. So if we use this mean field theory, we can very nicely reproduce the ordered phase and the disordered phase and the critical temperature between them. I mean, we ignore quite a number of details or local fluctuation. We actually completely ignore this local fluctuation, but thanks to this approximation, we actually have this result. And perhaps more importantly, so in this case, we can actually write down at h is equal to 0. This is tangent hyperbole of t, tc over t and 0t. And near t is equal to tc or tc minus, m value is quite small. So we can actually use this result. Q. And there are higher order term, but we will ignore that. And by calculating this, we can actually get this one as plus minus. And we can actually get this beta exponent with the 1/2. Because that would produce the square root of tc minus t. And this critical exponent is really important. So it's kind of amazing that using this approximation, we can get this critical exponent with this simple Taylor series expansion.